Next speaker will be Nick Tudor from D-Risk Limited. He's a director. He will brief on the topic automatic formal verification. Nick is the founder and director of D-Risk, which develops automatic FM-based verification tools for markets such as autonomous systems and cybersecurity, automotive, and aerospace. The tools cover requirements to binary with little expertise required to use them. And he's a key author of DEVO 333, the FM supplement to DEVO 178C. Yeah.
Thanks. So if that was sublime to ridiculous, I'm not quite sure what this is going to be. So somewhere in between, I hope. My apologies if my voice goes halfway through. I woke up at 3:30 this morning thinking, shall I actually come today? It's quite bad. What we're going to do is just have a quick canter through the kind of things that we've been doing over the past few years, really. So automatic formal verification. Actually, we could cut this really quickly. You've got the slides. If you want to get to a coffee really quickly, we could do any questions now. Or shall we do this as well? Okay, I'll do this. Okay, so just going to start with the whole process of systems and software certification. So you want to do something, and then you're going to get a system architecture to do something that you actually implement those set of requirements, and then you've got to verify that it's done that. And then part of those system requirements you can take into software, and those all ripple down into some form of design. And by the way, it doesn't have to be a waterfall kind of model. It could be any model you like. They're all the same. And then, of course, you have to do the verification at this level and all the levels all the way down. And unfortunately, that's insufficient, particularly from a 178 perspective. Then you also have to do that coverage stuff, which is obviously test-based. The problem with all this, of course, is that whilst this gives you the evidence for safety and security, it can be as much as 80% of your cost is doing the verification if you've got this process wrong. So that's what the problem is. But why are we doing this as well? Because I don't like the term bug, by the way. A lot of people talk about bugs, a bit too cute and cuddly for my liking. Somebody's made a cock up somewhere. I hope that translates. You've made an error. Okay, that's you have made an error somewhere, right? It's not a cute and cuddly furry creature that's got in there and got fried. So all humans do is introduce errors, but wouldn't it be good if it was possible right from the outset to say, well, this is what I want my system to do. Does the design actually satisfy that system before the project got going? Know that that was the case. That'd be kind of cool to do, wouldn't it? Instead of finding out at the end, of course. And then when I've taken that design, does the next step, does it actually, when I implement it, actually put it into code, does the code actually satisfy that design? Without doing loads and loads of review and test. And then, of course, all that evidence has to be then met, used for meeting the likes of the safety case or the security case. So that would be good. I would hope that would resonate with everybody here. And you're all still awake, which is good, including online. Right. So deterministic behaviour then. We hear an awful lot of people talk about, is it deterministic? Well, now, my view is that the deterministic behaviour of a software-based system is that there's a boundary that you have of it, right? And that boundary is defined by things like the requirements, because that's what I want it to do, environment, physics, all that sort of stuff. Now, if we take the white space of the board to be the universe, which I'm taking to be and everything in it, then the deterministic boundary, the behaviour, is some subset of that. So it's not in every single case in the entire universe. So everything in there then must be deterministic. And the reason for that is that these are all ones and noughts. It can only ever be a one or a nought until somebody puts a hand up and says, what about quantum computing? Get out. Right, so we don't want any of those ones and noughts to actually leak out. We want all the right ones in the right order, and we don't want anything to interfere with that in any way whatsoever. So what we do is we actually probe that boundary. This is called testing, of course. We probe that boundary, loads and loads of testing, and we poke around inside it as well, and that's called coverage. And we make sure that we've got all the right ones and all the right noughts, all in the right order, right? And there are nothing else extra that we wanted. And that's what we do. That's what the standards are all about. So it's a bit difficult when it comes to something when people say, well, hang on a second, I want to put some AI in here or some machine learning or something like that, because that's not deterministic. Yes, it is, because it's still a one and a naught. So this is the 0178C, the verification objectives. It's multicoloured. I hope you're not feeling too rough after lunch because it's quite technicoloured. And there's an awful lot of effort needs to go in to do all this. That's where the 80% comes from if you're doing sort of level A kind of software. It can be as much as that. And you've got all this stuff like the untraceable object code down here. So what we know is from aerospace is that there's been no hull loss. That means accidents, people dying as a result of software in any civil aircraft, which is quite a nice sort of tick in the box, really. None whatsoever. So that's good. So DR178B seems to have worked, and DR178C hasn't done any changes to that. So this seems to work, but people think it's expensive. Well, it is if you do it wrong. So the current approach then really is assuring this boundary. So I'm just going to try this into a slightly different format. You've got your system requirements and you've got your safe software requirements. Then you do some development evidence to try and meet those particular objectives. That's great. There's the verification evidence for doing that review. And similarly, you then go on to the next step and you develop your software design, and then you get some more evidence out of that. And then you go into the coding and you do some code, and then yes, you get some evidence from that as well. And you go into the next step, which is actually compiling it, and you do some more evidence from that as well. So that's the whole approach. And what we're trying to show is by doing a formal verification, if I can formally verify the boundary of this and make sure nothing can go in and nothing can go out, then I can actually, because formal actually means subject to mechanical analysis, put a machine in way of doing all this sort of stuff for me. But I just need to be able to show that that boundary is not violated in any particular way. So I think we've seen this before. Any questions? Good. So here's the DO333 objectives. So you notice that there's a subtle difference. Firstly, we've got the FM word in front of the abbreviation here. So we're specifically referring to a formal methods objective. And we've also done is we've got this thing called property preservation. You have to go and get DO333 to read what that really means, but it basically says the executable satisfies the intent of the source code. And then over the top right there, the coverage that's there, it's got less objectives, or sorry, fewer objectives to be specifically precise about this. So we have fewer objectives, and you can see there the bottom one, FM 7.5-8, structural coverage. That's removed the need to do MCDC testing and the like. Okay. So what that's basically done is says, well, hang on a second, what are you doing here? What you're saying is that I don't need to do that. Yes, we're right. The specific intent when I asked the group says, if we can't get rid of the need to do MCDC coverage analysis, it's not testing, by the way, it's coverage and analysis of the testing, then we have failed. So we need to do something about that, and that's what we did, and we had managed to get this past plenary. So again, please go and have a look at the document and see how we managed to do that. What that implies is that there's a proof that can be done then to have my executable in some way, shape or form. But what we also have to do, and we thought this was really rather good, cool is another way of people described it, we actually have to justify what we're doing and why we're doing it. So this formal method then, why is it the right one to be using for the things that you're trying to show? Which I thought was quite good, as opposed to saying, so you're using this bug hunter and you're trying to claim some credit for certification as a result of using it, are you? Is it just because of one of those things that you've got in your toolbox that the company's bought for you and now you want to claim credit for it? Okay, so we actually say there's an objective. You have to justify the use of this particular formal method, amongst a few other bits and pieces in those objectives. So that's what we did when we wrote 178. So obviously this is what we've been doing in de-risk. Is the idea is to remove the opportunity for humans to make errors, and that's very difficult. But if we can manage to hide it behind something that's very accessible, tick VG. And what we're trying to do is this line here really. If you don't need to know how a laptop works in order to be able to use it, so you don't need to know how the four methods work in order to be able to use it. So what's the approach? This is quite straightforward. So looking for independence, that's a key word. Looking for automation, of course, high assurance. So what we've got is a development artifact one, language one, and then something, a person or a machine, translates that into another artifact. So it could be English into design or design into code, whatever. And all we're going to do is have an appropriate mathematical representation, and then we're going to do an automatic proof of some sort between it. That's it. That's very simple, isn't it? I don't know why anybody hasn't done this, really. So, okay. This is the hard bit. Right, so what we've got is this is what we've been doing. So here's some software requirements that have been handed down to us by the system requirements. So that's typically done by a review. We're going to get rid of that. This is work in progress. We've got a very catchily named DRE, De-Risk Requirements English, when actually an editor that forces you to only write requirements that are verifiable. And in DR 178B, it actually says, and people completely ignore this, words to the effect of, please don't do anything that's not verifiable. Up to you if you do, and then they completely ignore it for the rest of the standard. And the same text is written in 178C, and that's why we've got people want to do things in Java or C++ in airplanes, which is ridiculous. So if you manage to do that, then we can claim some of the objectives for FMA3, and there's 7 to be got there, and I think we can get 3 of them. And then the next one is ModelWorks. We're about to enter a bunch of trials in aerospace for this, and that adds to some of the FMA3 objectives and covers all of the A4 objectives, partially or completely. So that's automating away all the review between design, in this case in Simulink and Stateflow, against some English language requirements. So this is the control systems domain we're targeting at the moment. And then we're going to auto-code, obviously, because people really don't want to type these days. So auto-code and then automatically prove, again, abstracting to a formal method to do that. And then this is the cool one right down the bottom, and you'll see why it's cool in a second. This is called Fever, and basically compile and then show that the object code satisfies the executable, and that's done through again, abstraction to some formal techniques. And the reason it's cool is because there's a little grey area over there called table A7. So, and there's these 2 blue lines coming back up here to design and requirements. Now, if you've done all of those 3 things in a formal way, then you can claim the credit automatically as a byproduct of doing the approach. That means you've then got rid of doing MCDC, etc., which I hope you think is cool. So that's what the plan is, and some of this has been done already. So, tick, yeah, definitely did that one. And tick, yeah, we're going to do that. And of course, because I helped write the standard, I hope we're going to comply with it. So some projects then. PICASSOS, this is a program we finished just over a year ago in automotive. Here's some results. So this was what can I say about this? Electric charging vehicle. There's one vehicle manufacturer on here which recently launched an electric charging vehicle. I can't say that we were involved in it particularly, but what you can see is there's a benchmark against no tools against our competitor, and the green is ModelWorks. And you can tell there's 7 different things on there. I'll come back to that in a second. We ran out of time to do that particular example. And again, this is all A still D stuff. These 2 examples here, they were done in 2 different companies. So just to tell you exactly what's going on here, there was 48 errors seeded all the way through this. So we need to make sure we could capture the types of errors that people make. And we wanted people who had done this not to be the same people who were doing the Simulink Design Verifier or the ModelWorks work. So what you've got is 3 sets of people going on here. And those particular example, that's 2 different companies. So there's 6 people doing work here. And the reason they're in the gold colour is because that's gold dust for us. That basically says that completely validates the experiment and the results we're getting from it. They're not exactly the same numbers, by the way. I've actually got the numbers from this. And this was not done with us. This was completely independent of us. So that's showing the benefits there. What also shows is the existing tool doesn't seem to give you any benefit in certain circumstances. In fact, it makes it worse in terms of the time. And then right the way across the board, you'll see a whole bunch of the savings benchmarked against the baseline. And what we say is, because obviously this depends on your processes that you've got at the moment, it is feasible to achieve 80% savings. Actually, it's more than that. Because this area now is much more automated, and that's the English language aspects that have been done in a much more tractable way. So there's a savings that can be made. Let's have a look at some complexity metrics. I accept that the Simulink metrics for complexity is not the best, but that's the only one we've got. So this is benchmarked against the baseline, and basically we think that's a curve. So intuitively it seems to be a curve. The more complex it gets, the harder it is for people to do stuff. And then if you bring in SLDV, we also think that's more or less a curve as well. Obviously slightly lower because there is some automation going on. What we would like to have had is something that was sort of way over there in the centre of Reading or something. This ends up being flat, more or less, because it's fully automated. The verification is just you capture the English and you capture the design, done. So that's pretty good. Where else have we used this? Well, this is an autonomous boat, and you'll see in a second some stuff we did with this, basically on a decision-making system to show that this always complies with the rules of the sea. So it will behave in terms of collision the way which another sea user would expect it to behave. So what we've got is a pop-up target. I'm going to hopefully this is going to work. Yeah. So a pop-up target is going to appear, and the blue is us. That's the USV. It's going to encroach that blue zone. So the behaviour you have to do is what's called collision mitigation here. We're assuming that it's going to have a crash, and ramming water into the hole is a bit Titanic-ish, so we have to stop. And the other reason I think is you have to exchange insurance details. Well, that could be just automotive. So there's a whole bunch of simulations. I just want to show you we had actually done something like this, and I got some video of that at sea, which is fun in the Solent, I can show you. Sector, the whole premise of this program is to reduce the cost of aerospace software, and they want to use formal techniques to do that as much as possible. And those of you here last year, Mike Bennett, who's the lead from that Rolls-Royce, gave a good overview of what was going on there. We're about to put the requirements editor and ModelWorks tool into trials with Rolls-Royce and MBDA. What else have we done? Well, there's two swarming projects here, which we finished about this time last year, actually. And what we showed is that each individual autonomous vehicle, vessel, whatever it happened to be, they had to comply with the rules of the sea, but they had to cooperate with each other. That's a swarm. Then can you show that they behaved the way the swarm would behave? Would the swarm maintain coherency? And what we showed was, yes, we could do that, and we could use exploration of failure behaviour. And what we showed was we could verify the behaviour of an arbitrary size swarm, but there were some constraints on that. How long does this sort of thing take? Well, I think, that's 1 billion states there, and it took about 10 minutes. So it's scalable. And actually, it only cost about £1.50 to do that by using a bit of cloud. We're now doing a similar sort of thing to USmooth in the air for beyond visual line of sight. So we're going to fly 2 UAVs at each other at the end of the year, and there won't be a loud bang, I hope. And we're exploiting some of this sort of work in the security domain as well, which I won't go into for obvious reasons. So lots of markets available to us here because it's just software, isn't it? We can make these sort of savings. It is automated. You don't need to be a rocket scientist or a brain surgeon to do this. And we're developing lots of different types of showcases to actually show that the technology works. And then if you want to buy some, please come and see me. Thank you.